Hello, everyone. Thanks for joining my presentation. I would like to talk about optimization models for pickup and delivery problems with reconfigurable capacity. This is a joint work with my colleagues Giovanni Lo Bianco and Chengyu Tao with my advisor Chris Beck at University of Toronto. This problem is inspired by a real case in northern Canada. There are 120 remote communities in northern Canada that require air transportation for their basic human needs, such as access to healthcare or food. Northern Canada covers around 48% of Canada's land, but it only has 0.5% of total population. This vast area with limited population inspired Northern Air Services to use flexible aircraft for transporting both passengers and cargo. These flexible aircraft have removable seats that can be removed to create more space for transporting cargo. For example, in this example, if we want to transport 4 boxes of cargo, we only have a space for 2 boxes of cargo. Therefore, we remove 2 seats and we create a space for this extra cargo. We define this novel problem. In this problem, we are given cargo and passengers that need to be delivered by flexible aircraft that has removable seats. And by removing of each seat, we can pack more cargo. We use parameter L. So when we remove each seat, we can in fact pack one box of cargo, which equals L kilogram. And our goal is to find a minimum cost tour while delivering all goods and passengers from their origins to destinations with the possibility of reconfiguring the aircraft capacity at each location. Here is the example of this problem. We have the depot of V0, and our initial aircraft configuration has 6 passenger seats and space for 2 boxes of cargo. One possible solution is to first visit location 3, pick up 4 passengers, then visit location 2. We still have a space for the green commodity. Next, visit location 5. Now we can deliver the green commodity. And after visiting location 6, we can drop off the blue commodity. Next, we're going to visit location 1, but it has 4 boxes of cargo and we don't have a space for that. So we will remove 2 seats, and we then will visit location 4 and drop the purple commodity and then return to the depot. So the initial aircraft configuration and the final aircraft configuration would not be the same. Next, in this presentation, we will cover the methods we use to solve this problem. So this is an NP-hard problem, and we need optimization methods to solve it optimally. One of the methods we use is CP model. The idea behind the CP model is one machine scheduling problem, where tasks or visits of aircraft. Setup time is the distance between 2 locations with a service time of 0, because there is no time associated with the visit. And we define different types of variables. The first variable is interval variable that represents visits to all the nodes. Pi, which is a sequence variable and represents the order of the locations that the aircraft visits. And SI is the number of seats picked up or dropped off at each location. In this Gantt chart, we show the idea behind the CP model. The rectangular on the time horizon shows the visits of the aircraft, and each 2 visits are separated by the distance between the corresponding locations. The orange line shows the available cargo space. It starts from C tilde 0, which is the initial cargo space, and then at location B2, it reaches to 0 because we have used all the space for cargo by picking up both the green and blue commodity. And then at location B4, it increases because we are dropping off all the, so after dropping off all the commodity and also removing seats, we are actually expanding the space for cargo boxes. Similarly, the blue line shows the number of empty seats. Again, we are starting from the initial number of empty seats, and then as we progress, it is decreasing because we are using that space for transporting passengers. But then at location V1, even though we are not transporting any passengers, again, it decreased because we removed 2 seats. And the pink line shows the total number of seats. And again, the total number of seats was fixed throughout this trip, except at V1 that we dropped off 2 seats. So now we are ready to see the CP model. These are the variables that we explained. Visits to each location is shown with interval variable, and number of added or removed seats is shown with SI variable, and aircraft tour with the sequence variable pi. We need to have a constraint that makes sure we have a valid tour, is no overlap constraint. So this constraint makes sure that the sequence of interval variables, every 2 of them are separated with the corresponding location of the corresponding location. Then we need to make sure that we pick up the commodity before dropping off. So X and N plus I is actually the corresponding location to the delivery location of commodity I. And we need to make sure that we first visit location XI, then XN plus Y. And then we need to make sure that our first and end locations are the first and end point of depot. So in the sequence variable, the first location is X0 and the last location is X2 and plus 1, which are both the depot locations. And finally, our goal is to minimize the total travel distance. So we need to make sure that the end time of last visit is actually minimized. Now we need to make sure that we are not exceeding the available capacity. So we have the cumulative function for the available cargo space, which is shown by C, and it is starting as C tilde 0, which is the initial capacity. And as we proceed this tour, we are reducing this cargo space if we pick up cargo or if we pick up passengers, if we pick up seats. If we're dropping off seats, then SI would be 0, so this will be added to the available cargo space. Similarly, we have a cumulative function for the number of empty seats. And again, it starts from S tilde 0, and as the travel proceeds, if we pick up seats, it is increasing. But if we pick up passengers, it is decreasing because the available empty seats is reduced. And finally, we need to have a cumulative function for the total number of passengers. Again, initially it has S tilde 0, and as the trip progresses, if we picked up seats, SI is positive, so the number of seats are increased. But if we drop off seats, the total number of seats would be decreased. And capacity constraint makes sure that always the total number of seats are less than S hat, which is in our case number 6, because that's the maximum capacity for seats. The other model that we use to solve this problem is called domain-independent dynamic programming model. It's a new model that formulates the problem as a dynamic program, but uses dynamic programming description language to solve it, which is inspired by AI planning. So instead of writing a problem-specific algorithm, we are using generic algorithm to solve it. And it uses recursive equations to define the problem. And the DP models consist of state variables, transitions, and target state. So we designed 2 DIDP models, 2 transition and 1 transition. Here I'm going to only explain one of them, the 2 transition model. So it starts from a tuple that has unvisited locations, current location, current cargo and current seats and current passengers. And as we trying to solve the problem, we are moving from this state to another state by using transitions. In this problem, we can have two types of transition. We can either move the aircraft or add or remove seats. So if we remove the aircraft, we can see the unvisited locations from only having location 4 would be empty because we are visiting location 4. So the current location would be 4, but the rest of variables would be the same. But if we decide to add or remove seats so the unvisited locations wouldn't be any different, but we are actually changing the current passengers and current seats. So in this example, we are from having no cargo, we have 4 boxes of cargo, and we are dropping off 2 seats. But it's not possible to distinguish between these two transitions in a state space graph. That's why we need to have a flag variable to tell us what to do in next transition. So a flag variable 0 tells us that next we're going to move the aircraft or not. And the rest are similar. So just when it's 0, we're going to pick up or drop off seats. So we make seat changes decisions. And then again, as we mentioned, the unvisited locations wouldn't be different, but the decisions regarding cargo and passengers would be different. And next, we're going to move the aircraft. So we're going to have different options of which location to visit. And the set of unvisited locations would be different. But the decision regarding the changes of number of seats wouldn't be any different. And we need to flip the value of our flag variable. And then finally, decisions regarding seat changes. So this example shows a transition from going from location B0 to B3. So first we're going to visit location 0. So first we won't make any decisions about seats. Then we're going to visit location 3. And again, we won't make any decisions regarding seats. And again, we're going to move the aircraft. So now we can define the model formally. So as we discussed, we have constants that are inputs of the problem, and we can define them earlier than giving the problem to the model. And we have state variables that are used for this model to solve the problem. So we have state variables, as I explained, set of unvisited locations is shown by U. I is a current location that is shown by I. Alpha tell us which type of transitions we are making, and pi shows the current number of passengers in the aircraft. Q, the current number of boxes of cargo, and S, the current number of seats. So we're going to define a function Z, U, I, Q, pi, S, alpha, which has different, which can have different values based on the variables inside it. So if we have visited all the locations, meaning that U is empty set, and alpha is 1, it means that it's time to return to depot. So from the location I, we're going to move to location 2n+1, which is the depot. If U is not empty, but alpha is 0, it means that we need to make decisions regarding seats. So we're going to choose delta. So we're going to make valid decisions regarding delta. So delta must be in T, which is a possible seat changes based on the current capacity of the cargo, current capacity of aircraft. And the function Z would be from UIQ pi would be UIQ plus WI, because WI is how much we have, how many cargo boxes we have picked up. And similarly, we can calculate the rest. And if U is not empty, but alpha is 1, we're going to make decisions regarding which location to visit next. So we have to take into account the distance from our current location to the next location, plus the location J is now visited, so it will be removed from unvisited locations, and the flag variable will be flipped. And again, J must be from possible locations, so we need to define a set R that shows which locations are valid. And finally, our goal is to compute target state. Because we are solving this model recursively, our target state is basically our initial state. It is when the unvisited locations are all the locations, and we have not picked up anything, and the number of seats are the initial configuration. So finally, we define the mixed integer programming model based on the existing compact two-index model for pickup and delivery problem, which is called location-based mixed integer programming model. And it uses 4 types of variables. It uses variables for aircraft tour, xij, and ti. It uses si variable, which is about seat decisions, and variables regarding cargo space and cargo boxes, and empty seats and passengers. xij is a binary variable that is 1 if edge ij is traveled and 0 otherwise. Ti shows the rank of location I on the tour, and si is for the number of seats added or removed. So if si is positive, it means we added seats at location I. If it's negative, it means that we removed seats. ui is the available cargo space, and yi is empty seats on arrival. Pi is number of passengers on the aircraft, and qi boxes of cargo on the aircraft. So with these four constraints, we are making sure that we have a valid tour, and with the last two of these 4 constraints, we make sure that we don't have any sub-tour. And our goal is, again, to minimize the total travel distance. And we need to make sure that we first visit the pickup location, then the delivery location. And then we're going to have some capacity constraints to make sure that we are not adding seats that we don't have a space for, or we are not picking passengers or cargo boxes that we don't, again, have a space for. And next, we need to make sure that the relationship between empty seats and available cargo space is valid. So we are not exceeding the total capacity, which is K, capital K, that is the total possible space for passengers plus boxes of cargo. Then we're going to have upper bound and lower bound on empty seats and available cargo space. And next, we need to force passenger and cargo demand, and upper and lower bound on seat decisions. So we cannot remove seats more than what it is actually on the aircraft, and also we cannot add seats more than what it is available at airport, or we cannot add seats more than total number of seats on the aircraft. And finally, we're going to have constraints for variable domains. Next, I'm going to explain the experimental results. We tested these models on randomly generated instances with commodity sizes from 4 to 20, which approximately reflect the problem instance, the real problem. And with 10 instances per each size, we solved this model using Groovy Optimizer and CP Optimizer for CP, and DID-PPY for DIDP models with complete anytime beam search solver. With a time limit of 600 seconds, we got this results. So this graph shows the number of solved instances that proved and found optimal compared to the number of requests. So as we can see, for the smaller number of requests, CP model was able to solve the instances, but for instances of size larger than 6, CP model was not able. but MIP and DIDP was able, with DIDP performing best. And in terms of mean runtime, where we chose 10 times time limit if for instances that no optimal solution was found, we see that again DIDP performed best with lower minimum runtime, but CP with higher mean runtime. And we compare the solution qualities. We can see that DIDP models found optimal solutions very fast, found these solutions very fast, but CP model was not able to find solutions very fast, and it was actually performing worse. And in the case that the model did not find a feasible solution by the time, we use an upper bound MIP model and to calculate a non-infinite measure. Next, I'm going to present conclusions and future work. So as I explained, we developed two MIP models, two DIDP and a CP model, and also an upper bound model that solves a restricted version of the problem. And we use that to warm start our MIP and CP models. And we compared these 5 models and 3 warm started models on randomly generated instances. And we saw that DIDP models perform best, both in terms of number of solved instances and average time to solve them, and CP performed worse than MIP for solving instances. For large instances, however, none of the models were able to solve the instance. As a future work, we would like to consider multiple aircraft with predefined schedules. Therefore, we can have tour in advance, and then with a given tour, find the best decisions regarding seats. Also, we would like to have a more realistic representation of cargo size. So currently, we consider that all cargo boxes have the same unit size, but in reality, cargo can be shipped in many different forms and sizes. Also, currently, we don't have any travel time restrictions for passengers, but again, in reality, some passengers maybe need to be reached earlier than others. And finally, we need to also consider handling and storage cars for seats. Therefore, we make less decisions maybe regarding changing of the seats or storing them in airports. Thank you so much for your attention. If you have any questions, you can email me your questions. Thank you.